Hey folks, happy Monday, happy March. Very excited. The weather has really turned, and even though it's cold today, we should be getting highs in the 40s and 50s. Also, a little side note, it is my birthday month, so I have a particular fondness for March. So today we start the second half of the unit, and we're going to dive into vectors. For those of you studying physics, you're probably like, woo, vectors. Do know that mathematicians look at vectors a little differently than scientists do. So just pay attention. I know it's really this time of the year, you want to just go with what you know. But like I said, we do think of them a little bit differently. So a vector has magnitude. Magnitude you're going to want to think of as a length. And then a direction. So that's usually an angle. It's represented by a directed line segment. So look, we're going to be drawing little rays is what they're going to look like. So like a line segment with an arrow at one end. Component form, I love component form. It's the horizontal change and the vertical change. And it's written with like the less than sign and the greater than sign. So not to confuse it with a point. Right, so let's just dive into some examples so you can see what the heck is this all about. So sketch vector v, if vector v equals -6, -8. So what I'm going to do on my grid is I'm going to plot the point -6, -8 first. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. There's the point. Now, mathematicians like to have our vectors in standard position, which this one will be in standard position. Starting point is actually going to be at the origin. Ending point is going to be that -6, -8. So we have this starting or initial point. In fact, let me pull out a different color. I'll call this initial point. And then where we ended, that is called the terminal point. Kind of like if you think of an airport terminal, kind of where you end your trip. I know it's also where you begin your trip sometimes, but think of it as where you end your trip. So this would be that vector v in standard position. So first question up is how the heck do we find the magnitude? So it's looking for this length. So let's talk length. So magnitude of vector v equals the square root, and you might be going, oh no, square root. Well, if we're in component form, it's going to be that -6 squared plus -8 squared. So not as bad as it may seem. So this is going to give us, let's see, underneath the square root, we get a 36 and a 64. Those add up to 100. So the length of the vector is 10. All right, direction is a little bit harder, right? Because we want to talk about the fact that that's pointing down there. So first, we need to create a little bit of a right triangle. So we get a different color out. I want to find this angle here because then my direction is going to be all the way around. So remember, I know that this is a 6 and this is an 8. So I can use tangent. So let's do a tangent of theta equals 8/6. And at this point, I'm going to need my calculator, right? Because I need to do tangent inverse of 8/6. So let me pull out my calculator, do tangent inverse of that. So I get an angle of 53.13 degrees. Now again, the direction, it has to account for the fact that this is over 180. So I'm going to take that angle we just got and add 180 to it. And so my direction is 233.13 degrees. So we were given the vector in component form. and we were able to find the magnitude and direction. We're going to be able to go backwards, by the way, given magnitude and direction, find the components as well. Okay, so let's move on to number 2. Notice for number 2, it tells us that initial point and that terminal point. So let's plot them. So this is where the vector is starting. And then -3, -5 is where the vector is ending. Okay, as a mathematician, the thing I really don't like about this is it's not in standard position, meaning I'm not starting at the origin. So here's what I'm going to do. I am going to basically take my terminal point and subtract the initial point. So what does that mean? My vector is going to be -3 minus 5 for the x component, and then -5 minus 1 for the y component. So that's going to be a -8, -6. That sounds familiar. Oh, it's like almost like number 1. So let me redraw this in standard position. So -8, -6. So there's my ending point, there's my initial point. So notice this blue vector I just drew, it should look like a copy of the red one, just kind of slid kind of down and to the left so that that initial point is at the origin. Okay, so it says write the component form. Well, we just got that. That's -8, -6. And then find its magnitude and direction. Okay, so magnitude, I guess we're calling this vector v as well. By the way, I'm putting an arrow over the v because typically the v is bolded, but I can't bold while I'm writing. So I'm going to do square root of -8 squared plus -6 squared, which I kind of know from up above this is going to be 10, but I'll go through the arithmetic, and I do get 10. Okay, direction. I'm going to create a right triangle and get this little angle here. So remember, I know this is a 6, this is an 8. So the tangent of theta is 6 over 8, which means I'm going to have to be doing a tangent inverse to get theta. So let me pull out my calculator and do that. So this is giving me that theta is 36.87 if I'm rounding to 2 decimals. But I have to account for the fact that this is really over 180 degrees. So I'm going to add 180 to that answer. And I get 216.87 degrees. Okay, so I hope vectors are making sense. They said they really do look like little rays, just kind of pointing. And notice we can slide them around so that we can put them into a standard position. So let's turn the page and talk about some equal vectors, opposite vectors, and then scalar multiple of a vector. So let's start, I guess, with equal vectors. We know that u would equal v if u1, u2 equals v1, v2. It's basically if their components are equal, the two vectors are equal, is what that's saying. I think it's a pretty intuitive concept. You'll be able to tell pretty quickly if two vectors are equal or not. Opposite vectors, well, if we have a vector u, where u1 or u equals u1, u2, then the opposite of u is going to be negative u1, negative u2. And then scalar multiple is actually going to feel a lot like what I just did. So if I have k times a vector u, that's going to be k times u1 and k times u2. So I'm really just multiplying the k to both components. So I would say all three of these are much easier than I'm probably making them look, but I'm getting definitions from your book. So I want to be clear about that. You'll be able to tell if two vectors are equal, and scalar multiple isn't as bad as it sounds. Okay, so let's take a look at some visual representations, because I know that some of you are visual learners, and so having something visual is going to be helpful. So I'm going to color code. So a vector equal to u. Well, what I'm going to do is I'm going to copy u, and then I'm going to lasso it, and I can put it anywhere I want. So if I wanted to put it up here, I could. That's a vector equal to u. And it doesn't really matter where it lands, by the way. I could have put it over here. So anywhere on the plane, as long as it keeps the same direction and it keeps the same size. So let's take a look at a vector equal to the opposite of u. So here's what I'm going to do. I'm going to copy u, but I'm going to switch my arrow. So let me lasso this and kind of bring it up. That blue vector represents a vector equal to u, but opposite. Now notice these points, this end point here for this vector that's opposite in part B. Its component form is -3, 4. Well, that's just taking that old vector u and multiplying it by a -1. So really opposite means points in the opposite direction. Okay, a vector equal to 2u. Whew. Okay, so I need 2u. So I really need to multiply by 2. So a couple ways we could do this. Let me do this in green. I could actually multiply my vector u by 2 and get the component form. So this would be 6, -8. Oh, there's that 6, -8 again, right? So this vector in green that I'm drawing would represent 2 times u. Now, another way I was thinking I could get this is I know that this blue vector is length of u, and then the original vector is length of u. So I could have drawn this whole length and put my arrow there and then moved it around. So that was the other way I was thinking about this. All right, and then a vector equal to -2u. Well, if you want to do the scalar multiple, if that seems kind of fun, you can do -6, +8. So -6, +8 would be up here. Notice that copies right over that blue vector, which was the opposite. The other thing I could have done is trace that green vector, put the arrow at the other end, and then moved it. So a couple different ways to think about this, depending on how algebraic or how graphical you prefer things. Okay, sum of the two vectors. When you're adding two vectors, you're going to call the sum the resultant vector. You may also see me in a problem say find the resultant. That means add the two vectors up. So graphically, I'm going to make a copy of vector u, and I'm going to lasso it and put it so that the beginning point is at the initial point of u is at the terminal point of V. So this is vector u here. And if I want to find the resultant vector, actually, let me do it in this red color. I'm going to start with where I started vector v, go all the way up to where I end vector u. So this would be considered my resultant. So v plus u is right there. Now, algebraically, if I'm doing v plus u equals, what should we call this vector? Let's do w. Algebraically, what this means, if I'm breaking down into components, is if I have v1, v2, and I'm adding it to u1, u2, that my result is going to be v1 plus u1 as the x component, and then v2 plus u2 as the y component. So x, y component. And that would be my resultant vector. Now, the reason this is lumped in with law of sines, law of cosines, is just to hint at a different way. The magnitude of this, vector v, and the magnitude of vector u represent kind of sides of a triangle. And if I know this angle here, I can do law of cosines to find the magnitude of vector w. So law of cosines can be used to add two vectors. I much prefer component form, but just know that that can be done. Okay, so now it says you practice. I'm going to leave the sketch to you, but I will practice some of these component form calculations because even though they are what you expect, it might help just to see some. So u plus v, what this means is I'm going to take the 4, 0 and add it to the 2, 3. So 4 plus 2 is 6, 0 plus 3 is 3. There's my result. 2 times vector v. This is going to be 4, 6 because I'm going to almost distribute that 2 to both components. And then I'll leave the last one for you as a little challenge, 3u minus 5v. See if you can do that. It's kind of combining what I did here in parts A and B. So I hope this helps give you a little intro to vectors. We're going to continue vector study on Wednesday when I see you. And your homework is number 30. So notice you're doing magnitude, direction. Do not worry about this standard unit vector form. That will come together when we talk on Wednesday. So don't worry too much about that. The rest of this should be fairly straightforward. All right, folks, have a great Monday. Happy March, and I will see you on Wednesday.